Testing. Hello. 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 Testing. Testing.
Hello? 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 Hello?
It's working. Here's some delay, but yeah, that will work.
10 seconds.
Okay, what's that?
Okay, very good. المفروض نخلص الساعة كام؟
Hi, Ahmed. I am Ahmed Mahmoud, and I'm going to continue the discussion on how big data systems actually process spatial keyword data. So now we introduced the queries, we introduced the query languages, and now how the big data systems and what are the approaches to process the spatial keyword big data. So there are three main approaches to process this big spatial keyword data. The first one is to just write an application on top of a general purpose big data system. And the second approach is to extend, add some more features or build on top of existing general purpose big data system. And the third approach is to just start a new system from scratch, do not extend or implement any extra features to the existing general purpose big data systems. So let's start with the applications on top of existing big data systems. So one work that addresses Boolean KNN queries over MapReduce. This work simply scans the entire data and builds a MapReduce job that answers the Boolean KNN query over this data. Just to remind you, what is the Boolean KNN query? It's a specific version of the top K query where objects are ranked based on the spatial distance between a focal point of the query and the location of objects. You would like to identify objects that cover all the query keywords. So this work simply creates a MapReduce job that the map face identifies all objects that cover the query keywords and the reduce and computes the distance between the object and the focal point of the query. And the reduce phase just get these objects, sorts them based on the distances, and produces the final result. No changes were made to a general purpose system or Hadoop or anything. The other work would be answering the m-closest spatial keyword group query. And as a reminder, this query retrieves a group of objects that have a smallest inter-object and inter-group distance that collectively cover the keywords of the query. So this work will actually produce an approximate answer. We'll use MapReduce, and this work will use the road network distance or graphs instead of using the Euclidean distance to answer this query. What this work does is it identifies a subgraph of the total graph of data that collectively cover the where nodes of this graph cover the keywords of the query, and edges between the nodes of this graph have minimum total weight. Which is called also the group center tree, and the work had a basic offline partitioning phase, and it partitioned the graph into overlapping partitions in an attempt to limit the data being scanned in the MapReduce job. This offline partitioning phase used some statistical approaches to identify the maximum number of edges or the maximum path lengths in a subgraph that may cover the keywords of the query. And then there will be an online MapReduce phase that will start by scanning data from partitions and then reading all of these partitions, constructing the graph in the reduce phase, and then build and scan all the possible solutions of the graph and find the one with the best answer. So again, there were no changes or building on the general purpose Hadoop system. One other work is that addresses the spatial keyword KNN join for wireless sensor networks. So wireless sensor networks are small nodes that have limited power, limited processing capabilities, and they usually have sensors to collect data from the environment. So if you really perform excessive computation on the wireless sensor network nodes, what will happen is that you will lose the power on the batteries of these nodes, and then they will become non-functional. So the proposal here is to answer this query, but to offload the processing from the wireless sensor network to the cloud into a MapReduce cluster. The query here is given a set R of locations with their query key, with a set of keywords associated with every location. And there is a set of sensor nodes. Also, they have they have focal points, and they have also a set of keywords coming from these sensors. And given that there is for this query, there is a fixed number, K, and the textual similarity threshold, we would like for every point R in the set R of locations to find the K nearest sensors that do not exceed a textual similarity threshold between the point R and the sensor. So instead of processing this expensive query over the wireless sensor nodes themselves, we will offload the processing into a Hadoop MapReduce cluster. In this work, what happens is that using MapReduce, there will be an inverted index over the sensor nodes set. And then in the query processing phase, we will use MapReduce, just read the set R, and then for every point R or object R in the set, we will use the inverted index to find the relevant sensors, and then identify from these relevant sensors, we will measure the distance, rank the most or the K nearest neighbor sensor to every point R. The second technique in the processing of big spatial keyword data is to extend general purpose big data systems, adding indexes to them, building more features on top of them. So one example system in this category is the ModiSense system. ModiSense is a platform for discovering points of interest and trending events from spatial keyword social data. For instance, if now there are so many people in the Hilton area talking about SIGMOD. So maybe there are tweets about this. There are people using their smartphones with their GPS traces that may create some traffic saying that the keyword SIGMOD in this area is a trending event. So this is what ModiSense does. ModiSense extends the HBase and uses it as a storage layer, and also uses MapReduce as the processing platform. This slide here describes the structure of the ModiSense system. The ModiSense has a front end or a user interface for desktop application and cell phone application. It has a storage layer that has an HBase cluster, and also Postgres SQL Server. So the HBase cluster is mainly used for data that has a high rate of updates, and the Postgres is used for data that is infrequently updated, that, for example, points of interest or blogs from users, but have high query rate. So the storage cluster here stores the social network information, such as who is friends to whom, the keywords of tweets being generated by users, where from the GPS traces, what are the popular places being visited. Okay. There is also a user management protocol that supports authentication for this system, and where actually the detection of trending events and points of interest is done using a Hadoop cluster by accessing the GPS traces, the visits, and the social information, and the textual processing of the social data. Another system is called Tornado, which is a streaming system, a distributed and adaptive system for the processing of spatial keyword data streams. And this system extends the general purpose Storm streaming system, which is a big data system in the Apache Foundation. The main idea in the Storm streaming system is to distribute the processing of spatial keyword data across multiple worker processes, such that data and continuous queries that are relevant to each other are located into the same worker process. So this figure here describes the processing model of the Storm streaming system. This system has input data streams that are called the spouts, and there are distributed worker processes, what Storm calls them bolts, and these bolts can be constructed or connected as a directed graph that will move tuples from input streams to the worker processes to maybe perform multiple levels of processing and then produce final output streams. So Tornado is structured as there will be data sources and continuous query sources, and then there will be an adaptive spatial keyword routing layer that takes this input data and distributes it to multiple worker processes called evaluators. These worker processes will have local spatial keyword indexes that will index the continuous queries and handle the incoming data, run them against the indexed queries to produce final results. There is another system called DSkype. DSkype answers the continuous top K spatial keyword queries over data streams. This work is a distributed version of the Skype system, which answers this query in a centralized environment. This centralized system is structured as we see in this figure. It's mainly, the main application is for top K publish subscribe systems, where there are some people that say, I am interested in some iPhone, cell phones, whatever, some keywords, and in their interest to also have a specific location. And whenever there are some ads being produced containing these keywords that are close by to the location of the subscription, they should be forwarded to the user or the subscriber. This system has a subscription index and a message index. And given that there are new messages, these messages will be stored in the message index, which is maintains for sliding window, counting sliding window. And these incoming messages will run against the subscription index, which can be seen as continuous top K spatial keyword queries to produce the final answer. However, when the number of subscriptions increase, it is no longer possible to support a high scale or a high number of these queries in a centralized system. So now the DSkype system extends the Storm streaming system by splitting the centralized system into multiple layers over the Storm streaming system. The same idea here is that you will have subscription spouts or data sources and messages spouts. And then there will be distribution bolts that are responsible of distributing the subscriptions or the continuous queries. Subscription can be seen as a continuous query. And the messages, which are the spatial keyword objects across distributed bolts or worker processes. So there will be some subscription bolts that will maintain the queries indexed, and there will also be message bolts that will contain the sliding window of spatial keyword objects, and there will be some aggregation bolts or worker processes that will aggregate the results from the distributed queries. And then these will produce final output. There is another system called BS2 stream, or publish subscribe stream, which is a distributed publish subscribe system that extends the general purpose storm streaming system for support of this continuous evaluation of the spatial keyword filter query. This system is structured as follows. There will be some data sources or spouts that will go through a layer of dispatcher or routing units, or these dispatchers will distribute the queries also and the spatial keyword objects across multiple bolts or processes, and there will be an aggregation layer that will group them to produce the final result of the queries. The third approach to handle big spatial keyword data is to build a big spatial keyword system from scratch and do not extend any general purpose system. One system here is called the news stand. And this system is mainly used to identify news from the web. So this system has distributed news crawlers over the internet, and it will collect these news, store them in a database, and also build some indexes over this data, these websites. And these websites, or the news from websites, will also go through a geotagging phase to read the content of the web page and to assign a set of locations, geotagged location, to this web page. Then there will be a clustering phase of these web pages to group multiple websites or multiple news documents that talk about the same event into the same cluster. And then from this clustering phase, it will go to a cluster focus that will assign this news topic to mainly specific locations, because a single web page may have a specific location that is the main area that had the event happen or the news happened, and there are some other non-highly important locations. So the cluster focus here phase is to identify the most relevant spatial location to this news, and then the results or this news will go back to the users. And here we see that there are no extensions to general purpose big data systems. This system has a user interface that will show that what are the trending news or the current news in every specific location. Here, this page shows another interface of the news stand system that shows what are the most prominent event happening in every spatial area. Another system is called the Twitter stand, which is kind of similar to the news stand system, But instead of reading news from the web pages, this system attempts to detect and identify news from tweets. This system has the following layers. The data input layer, which reads the tweets from multiple important sources from the Twitter framework. Seeders are people who are mainly tweeting, are known to be tweeting about news. The garden hose, which is a sample of the Twitter fire hose system, of the Twitter fire hose data source. And also, the Twitter API supports search for some specific keywords. So this system also uses some search features that identify tweets talking about news. And then tweets from the input layer will go into a classification layer. This layer will identify tweets that are talking about news from tweets that are not talking about news. And then from this phase, from the classification, there will be a clustering phase to identify tweets talking about a specific object, a specific event. And after this, there will be a geotagging phase that will assign one location or multiple locations to this event. And then these all will go to a user interface. So the scale of the Twitter data is large, and these will have distributed processes to consume the data and process them. So we can see that this is a kind of big data system that is distributed to handle this scale of data and in a distributed fashion. Similar to the newsstand interface, also Twitter stand has a similar interface to identify news that are associated to spatial locations. Another system called TagRead, which answers the following set of spatial keyword queries over microblogs. The spatial keyword filter query, the spatial keyword top K frequent keywords that are what are the frequent keywords in Twitter in a specific area, who are the most active users in a specific region, who are the top K famous users in a specific region, and aggregates how many, what is the most popular keyword, how many tweets were produced in a specific area, and the top K languages used while tweeting. So this system has the following layers. It has a user interface layer that will receive the queries and produce and show the results to the users. It will also have a query optimizer that from the query it will build a query plan to execute this query, and the query processor that will use some indexes, main memory indexes over the space, time, and text from the main memory, and then to produce the final result. And when the main memory is not large enough to hold all the incoming tweets, there is a flushing protocol that takes some irrelevant tweets, put them into the disk indexed to. And there is also, since this is a main memory system, there is a recovery manager that handles the situation when the one machine fails, what will happen. So we can say that this system can be seen as a big spatial keyword system, because this is a distributed processing platform. In the recovery manager, for instance, it uses replication of the tweets and the indexes across multiple machines, so that when one machine fails, all the indexes in the main memory remain in the memory of the other machines. And also, the tweet has spatial properties, textual properties, temporal properties, and other non-spatial textual temporal properties. So this system has indexes for space and time and text, but does not have indexes for user IDs, does not have indexes, for instance, for who followed, who retweeted about what. So to answer a complex query, he uses first the space and time and text indexes, and then, let's say, for a query such as top K famous users, there are distributed processes that scan data from these indexes to produce a final result. And this is the user interface of the Tagreed system. It also has a spatial map, and it will show the trending tweets or events and the keywords of these tweets also on the interface. Now we described the main approaches of processing spatial keyword data in big data systems. I'm going to discuss the indexing of spatial keyword data in big data systems, because indexing is an integral part to speed up the processing of queries. We can classify the approaches for indexing spatial keyword data into the following categories. The first one is spatial only indexing with textual filtering on the fly. And then there are some inverted indexing techniques, hybrid structures that uses both spatial and the textual index. And then there are, for the streaming systems, data stream partitioning across multiple worker processes. So let's begin with the spatial only indexing. There is a service called Tariq. Tariq is a service for the extraction of spatial data from OpenStreetMap. This service uses spatial only indexes on top of spatial Hadoop. Spatial Hadoop is a spatial only system that extends the Hadoop general purpose big data system with the spatial indexes that are either grid or R3 based. To find, let's say, roads or lakes or other types of objects from the OpenStreetMap data in a specific region, a query with the spatial properties is first submitted to the spatial Hadoop, and then textual filtering is performed on the fly. This is the user interface from the Tariq service. It has a map that allows to specify the interesting spatial range, and there is also a list of interesting textual objects that are needed to be extracted from this map. Another popular approach is to use the inverted indexing on top of the Hadoop file system. So there is one work that identifies the top K users in a specific region. And what is meant by the top K users? The top K users are the people who are talking and producing the most relevant and popular tweets about a specific topic. So when I tweet, I make an interesting tweet. Some people may retweet to it. Some people may respond to it. So this makes a tweet popular, and the individual who created this popular tweet becomes a popular user. In this work, tweets are stored into the HDFS. And to address this query, an inverted index on top of these tweets is added to the HDFS. So this inverted index uses mainly a hash map with a key and a pointer to the HDFS block that contains the tweet. What is the key that is used for the inverted structure is called a geohash. That a geohash and the keyword. So every object indexed or every tweet, it has a set of keywords. And for every keyword, it will be added to the inverted structure with a geohash. A geohash is an encoding of the spatial location of the object. This encoding is calculated from a quad tree. In an offline way, the quad tree structure is created, and the quad tree will have 4 children. For every child of the quad tree, there will be an encoding with 2 bits. These are 0, 0, 0, 1, 1, 0, 1, 1. And this is per level. Across the level of the quad tree, there will be, when I reach a leaf level, I will have a long code of bits. This long code will be transferred into, encoded into a keyword and attached to the term of the tweet, and then used as the key for the inverted structure in the HDFS. Another system that uses a similar idea is called the spatiotextual HBase. This system extends the HBase general purpose storage with an inverted structure. This system introduced 2 indexes. One of them is called the spatial and textual based hybrid index. This index creates an inverted list over the data, and it has a key, and this key is the keyword from the object, or for every keyword there will be an entry. For every keyword in an object there will be an entry in the table, and also there will be a key that is based on the Z order location of the object. So to insert an object into the inverted list, for every keyword, you get the Z order of the object, attach it to the keyword, insert it into the inverted table. One limitation of this approach, and the approach used in the previous slide, is that for every keyword of the object, you will have an entry in the inverted list. So when objects have multiple keywords, this will create an overhead in the space. So there are other techniques to handle this issue, which is to use a hybrid structure. This hybrid structure was also used in the spatiotextual HBase. And to avoid inserting the same object multiple times for every keyword, this HBase structure, spatiotextual HBase, used the co-occurrence of keywords across objects to create term clusters. So first of all, there will be some terms, which is an inverted list. And then the inverted list will point to term clusters for objects, for keywords that frequently happen with each other or appear in the same object together. And for all objects that are in the same term cluster, there will be a KD tree constructed for them. They will be indexed in the KD tree in a specific block for them. And for them, using the KD tree, they will find the Z order for the objects in this KD tree, and they will be inserted into the HBase storage. So objects will be accessed based on their term cluster and their Z order within the HBase storage. The Dskype system also, which we said before, it's an extension to the Skype system on top of the Storm streaming system. This system stores the queries of the top K spatial keyword queries which has a spatial location, focal point, and a set of keywords, and it is desired to identify, continuously report all the top K spatially keyword relevant objects. So these queries are indexed using the quad tree structure, and for every cell in the quad tree there will be an inverted list for all the queries included into the node of the quad tree. There is also one thing that we need to mention here. Since there are multiple processes in this streaming system that handle or store the continuous queries. So there is one interesting question. How do we distribute these queries across these worker processes? And actually this work, this studies the differences between these approaches. There are some variations are randomly distribute these queries across the processes, or collocate them based on the spatial proximity, or collocate them based on the textual, such that queries with the same keywords will be indexed in the same process. And this work studies the variations in performance using each and every technique of them. One work that extends the Spark system for answering the collective spatial keyword group query over road that answers the spatial keyword collective spatial keyword group query. And as a reminder, this query has a focal point and a set of keywords, and it is desired to find the group of objects that collectively cover these keywords that are having a small distance in this group, and also have us close to the query location. So this system has a hybrid structure from a grid structure and an inverted list. It will maintain the partition the space into grid cells, and it will also keep an inverted structure of the cells to keep track of which keywords that are contained within every cell. And to answer this collective spatial keyword group query, cells that contain the keywords are first identified and then scanned in the proximity of the query. And once these cells have been identified, the centralized version or the exact algorithm for answering this query is run against these data within these cells. Indexing in the Tagreed system, as we mentioned before, Tagreed has two versions: main memory indexes and disk-based indexes. The main memory indexes are spatial and textual and temporal separately. So Tagreed uses segmented inverted lists and creates an inverted list for each time period. For instance, it will have an inverted list for the time period from 0 to t, and another inverted list from t to 2t, and so on. Separate textual index for these objects. And also it will have the pyramid structure index in the main memory for the spatial properties. Once again, it will be partitioned based on the time period from 0 to t, and from t to 2t, and so on. And as we go down into the time, going backward, some of them will become irrelevant and will be flushed to disk. So the space is indexed using the pyramid structure, the text is indexed using the inverted list, and time is indexed using these partition time periods. And a similar idea is adopted for disk-based indexes, but with hierarchical structures. So there will be segments from days, and then when there are 7 days that are already done, they will be merged into segments of weeks, and 4 weeks will create segments of months, and so on. The spatial indexing here will be based on we'll use the R3 because it's a disk-based index. Main memory indexes will use the pyramid structure. And the last approach for indexing is the data streams partitioning. And we give an example here of the tornado system. The tornado system we mentioned before, it will have an input layer and then a routing layer and an evaluation layer on top of the storm streaming system. So tornado partitions the space into non-overlapping spatial ranges, and then data will go through one of the routing units to go to the evaluators. These routing units will also maintain the keywords of all the indexed queries within a specific process, such that when a data object comes to be sent to one worker process and it does not have any query that is relevant to the indexed queries, it will not be forwarded from the routing unit to the evaluators. So it will use the spatial properties and the textual properties to improve the performance of the tornado system. Next, I'm going to discuss some describe more related work into the area of the spatial keyword for big data systems. There is a system called disks, which is a system for the distributed processing of the group query over road networks. And this system partitions the road networks into node disjoint subgraphs. And then these data partitions are indexed in top or into HDFS, and the query processing is performed using the map reduce. So this slide here describes the structure of the disk system. It will have there will be this road network data stored in top of the HDFS system. It will go through a partitioner that will try to find relevant partitions, or it will use a partitioner API to partition data into the HDFS. It will be indexed here into multiple partitions, and then when a user has a spatial keyword group query, it will go through these indexed partitions to find the final answer, produce it into the user interface. All of these partitioning will be performed using, all this processing will be done by the Hadoop MapReduce system. And this is the UI of the disks system. It will allow you to identify the groups of objects that cover the query keywords. It will also give you multiple groups and allow you to compare these groups against each other. Another system called the Terrafly SKS Open. Terrafly is a system for querying and visualizing geospatial data, and it's a popular system that serves worldwide map requests from multiple countries and supports multiple overlays of this spatial data and street names, roads, and restaurants and services. The Terrafly's SKS Open is an indexing and query engine to identify the top K spatial keyword queries, to answer the top K spatial keyword queries over the Terrafly system. So the SKS Open actually uses the Hadoop MapReduce to build a spatial keyword index. So it does not run the queries over the MapReduce, but given the large amount of data, it wants to build an inverted, a spatial keyword index, centralized index. But it builds this index to reduce the time. It uses the Hadoop MapReduce. So in the MapReduce phase, in the map phase, it will be a partitioning phase to partition all of this data into multiple sub-indices, and the reduce phase will combine sub-indices together into a bigger index, produces the final result, as the final result here is to produce an index. And whenever spatial keyword queries go, they will access this index to produce the final result. So this is a variation of how this system uses the general purpose big data system, not to answer the query, but to build the index. The Nimbus service is a tuning service for Twitter analysis. So some companies actually would like to perform some analysis over the Twitter data, and they impose filters to identify the relevant tweets. And this service here to test the quality of your filters over the Twitter data. It maintains a subset of the tweets stored in a database, and it uses the Spark system to consume some of these tweets and build an index and index them. So the Nimbus uses the GNIP or GNIP PowerTrack query language we described before, and uses a database of tweets to check if the Twitter filter retrieves only relevant tweets or not, and measures the hit ratio of the specific tweet filter. This is the structure of the Nimbus service. It has Spark streaming actually to consume the tweets and index them. And it will also have, it will run the filters against the stored tweets to filter, to identify the quality of these filters. For instance, people talking tweets about Adobe will be this amount of tweets. Photoshop will get these tweets, and Adobe and Photoshop will give you these set of specific tweets. Now we are going to move forward to discuss some future research directions in the spatial keyword big data processing.
Okay, so now we'll talk about the future research directions. And this we will cover 4 fronts: load balancing in spatial keyword systems, benchmarking, pipelined evaluation and query processing, and then big spatio-temporal keyword processing. So we'll start with load balancing. So as we know, spatial keyword workload varies over time because of the distribution and the movement of the objects over space and time, and also the trending activities vary from location to the other over time as well. So spatial keyword systems need to be adaptive and elastic. So this is just an example of the day and night. So this is the front here for the day, and this is the night, and you can see that with time things the distribution changes as time passes. So load balancing, that as an example in Tornado, so there are evaluators. Each evaluator is responsible for a specific region in space. So because Tornado is a data streaming system, so whenever, let's say, this red region has high activity, so it decides to split this worker into multiple workers, let's say in this case 2 workers. So it designates an auxiliary bolt which will do the processing, an extra one, but because the resources are limited, it tries to find the slowest or the 2 bolts with the least amount of load and try to merge them at the same time. So it introduces 1 bolt here that will split the activity of a hotspot, but at the same time try to merge 2 low workload entities. So this is just one effort towards load balancing, but more work needs to be done in this venue. So load balancing and adaptive, there are definitely other issues for load balancing, whether it's for batch systems, disk-based, memory-based, they all need to be addressed. Also, we need to account for various types of spatial keyword queries. Some of them are more expensive than others, so the cost of the computation of the spatial keyword query itself needs to also be taken into consideration in load balancing, not just the data that's being touched and the number of queries, for example. Benchmarking. So there are several benchmarking proposals. For example, Berlin Mod or Jack Pine that are both spatial only. There are also relational benchmarks that are quite popular. We need spatial benchmarks, spatial keyword benchmarks that are general and not, so there are existing ones that, for example, focus on spatial social network analytics. So, and it also covers a limited set of queries. We need general benchmarks for big data systems. It needs to contain large data sets of spatial keyword objects. Also supports wide range of query types and support both streaming and batching. For pipelined evaluation and query processing, we need to be able to build or identify a set of sound and complete building blocks so that we are able to compose these building blocks minimally to construct any spatial keyword query at hand. So, for example, Atlas is one attempt towards that, but it's not shown to be sound and complete. Whether the proposed set is minimal or that has some redundancies, that also needs to be addressed. In terms of additional, so spatial keyword plus other features, for example, here we demonstrate the adding the temporal dimensions. So spatial keyword data is often associated with temporal attributes, like for example the timestamps of tweets. So we need further investigation on how to index spatial keyword or spatio-temporal keyword data in terms of indexing, query processing, expressibility of query languages, and efficiency in processing. So this brings us to the end of our tutorial. If you have any questions, you are welcome to ask them now.
Thanks a lot for the tutorial and covering all this work. And my question is about the types of queries that run on spatial textual data. So when we talk about big data, did some queries gain more importance with big data, or some new queries that just emerged because of big data, or are just like all of them the same queries, but we just have an additional challenge because of the size of the data or the velocity of it?
So that's a good question. The ones we presented in the tutorial are mainly the standard ones. Although the issue of scale, I think, is the new dimension. So I think being online plus scale, so scalability, I think, is the main challenge. I don't think that query types differ unless we focus on analytics, but analytics also, whether it's big data or small, can also be the same. So I'm not sure that there are new queries that are to be introduced given that we are in the big data realm, but I think the issue of scale is what counts here.
Also, many of these queries that we introduce are not even answered in the big data environment. So just we mentioned the main queries, but some of them are not even addressed due to the complexity of the processing to evaluate the final answer of this query. So this still is an open research issue to address non-addressed queries in the big spatial keyword domain.
Thank you for nice tutorial. And I'm interested in computational complexity. And so I'm, I want to know the complexity come from the complexity of a spatial query or textual query. So how do you think? So the complexity, which is a large portion of the chemical column?
So if we agree that it's the queries themselves, the types of the queries are the same whether it's for big data or not. So the complexity would not matter, but for big data in specific, it adds one new dimension if you have a cluster, a new dimension to the cost, which is the communication cost. So for example, once you partition the data, let's say for example, take the top K query, so or the K nearest neighbor mainly. So now if my data is partitioned and I have a focal point, then I need to compute the K nearest neighbor locally and then communicate the answer to some integrator that will put the K answers together and try to come up with the global K nearest neighbor. So I think the distribution part adds to the complexity of the operations, although we did not focus on it here. Yeah. Yeah. Any other questions? Okay, thank you, and hopefully that was useful. Thank you. Bye.